Did you know the universe is still expanding every second faster than we can fully explain? Settle deeper into your seat and let that thought drift through you for a moment. The ship's hull hums softly around you, a steady vibration that feels almost like a heartbeat. Console lights glow in gentle patterns, brushing the cabin with calm, shifting colors. Beyond the glass, space stretches in absolute silence, sendless, patient, unhurried. As you breathe out, let the weight of the day loosen. Tonight, you're not just traveling through space, you're slipping back through time, toward the first spark of everything you've ever known. Maybe you came here looking for quiet. Maybe you just want a moment where nothing demands anything from you. Either way, this journey belongs entirely to you. Let your breathing fall into sync with the ship's soft rhythm as the stars drift by outside. Feel your thoughts soften, untangle, and settle. As you float through this dark ocean, a single question begins to form, simple, but enormous enough to swallow entire galaxies. Where did all of this come from? It's the kind of question that sits at the edge of science and wonder, too big for any one mind to hold, yet impossible to ignore. How do you even imagine the beginning of time when time itself wasn't ticking yet? How do you picture the birth of space when there was no space to stand in? It's a cosmic riddle that puzzled scientists for centuries. But something changed in the early 1900s. Subtle, clandestine fingerprints scattered across the sky started pointing toward a truth no one expected. Bit by bit, the evidence whispered the same idea: the universe isn't still. It isn't fixed. It's stretching outward, growing, unfolding. And you're about to drift right into the heart of that discovery. Imagine the space between galaxies stretching, not like debris scattering from an explosion, but as if the very fabric of space itself is growing, everywhere, all at once. The idea must have been profoundly unsettling. For countless centuries, humanity had held on to the comforting notion of an eternal, immutable cosmos. It was simply their asterisk. Even the brilliant Albert Einstein, when first grappling with the implications of his own groundbreaking equations, famously introduced a cosmological constant to counteract this startling possibility of expansion. He didn't do it because the mathematics demanded it, but because the very idea of a dynamic, ever-changing universe seemed too strange, too unstable, too unsettling. He later confessed it was his greatest scientific blunder. Why does the universe always do this, challenging our neatest assumptions? But as more data streamed in, carried on the ancient waves of light, the evidence for a dynamic cosmos became impossible to ignore. In the 1920s, another astronomer, Edwin Hubble, made a truly transformative discovery. As you gaze out at the distant pinpricks of light reflecting on the viewscreen, imagine him studying the faint glow from far-off galaxies. He noticed something utterly unexpected. Their light was stretched, reddened, as if being gently pulled away from us. And the farther a galaxy was, the more pronounced this reddening appeared. It wasn't just a few rogue galaxies receding. All of them were, and the farther they were, the faster they seemed to be drifting. This peculiar pattern, this cosmic stretch, could lead to only one conclusion. The universe was expanding, not with galaxies simply flying through empty space, but with space itself gently growing, carrying the galaxies apart like raisins embedded in a slowly rising loaf of bread. It was a truly radical concept, a redefinition of everything, but the data spoke volumes. And if the universe is expanding today, then, logically, as we rewind the cosmic clock, it must have been smaller, denser, much, much hotter. Imagine a journey backward in time, where every light year we traverse sees the universe tighten, compress, becoming infinitely more extreme. This relentless reasoning eventually led scientists to a remarkable, almost poetic conclusion. If everything is spreading apart now, and that pattern holds true as we trace our steps back, then the universe must have once been compacted into an incredibly hot, unbelievably dense state. A state where all matter, all energy, every bit of space, and even time itself might have been squashed together, not precisely into a single, infinitesimal point, the classic singularity often described, but into a state so extreme that our most advanced physics begins to shimmer and blur, unable to fully describe it. This became the foundational idea for what we now understand as the Big Bang Theory. It's a somewhat misleading name, isn't it? A bang implies an explosion asterisk into asterisk space, but in reality, space itself was what was beginning. There was no sound, for there was nothing for sound waves to travel through, and no light in the way we typically imagine it. Instead, picture an unfolding of everything, everywhere, all at once, a moment when the universe wasn't expanding asterisk into asterisk pre-existing space, but rather asterisk creating asterisk space as it expanded. We should pause here, just for a moment, as you feel the subtle shift in gravity, a gentle reminder of our journey. This is precisely where the guiding light of science reaches its current horizon. The Big Bang Theory doesn't actually describe the absolute beginning, the exact inception. Instead, it offers a magnificent framework for everything that transpired asterisk after asterisk that initial cosmic expansion began. It helps us understand how the universe evolved from that impossibly early, fiery state into the cool, structured cosmos we peacefully observe today. But the precise moment of beginning, the true nature of time, space, and causality, asterisk before asterisk, that expansion remains cloaked in profound mystery. We don't yet know what, if anything, preceded it. Perhaps we never will. Just float with that thought for a moment. But let's gently drift closer, examining what we can articulate about this earliest phase of the Big Bang, not as an abstract notion, but as a series of physical events. We don't truly commence with a classic singularity, not in the way it's often popularized as an infinitely small point. A true singularity implies infinite density, infinite temperature, infinite curvature, and while Einstein's general relativity seems to hint at such a point, quantum mechanics, the physics of the very small, doesn't quite tolerate such infinities with ease. What we're truly encountering here is a frontier, a boundary beyond which our current understanding simply breaks down. It's not necessarily because there's nothing there, but because our mathematics, our scientific language, no longer possesses the vocabulary to describe it. What kind of secrets does that frontier hold? As you drift here with me, the soft hum of the ship's engines, a constant, comforting lullaby in the recycled air. Perhaps you're wondering how far back we can truly reach into the grand tapestry of existence. Feel that subtle vibration through the hull. It's just the steady breath of our vessel, carrying us silently across the velvet void, past distant starlight, reflecting like scattered diamonds on the console's gentle glow. We're going to journey to a time almost beyond imagination, to the earliest flicker of what we can meaningfully describe, a whisper of creation known as the Planck epoch. It's a moment so profoundly fleeting, just an infinitesimally tiny sliver of time after the universe began its vast expansion, a mere 100 million trillions of a second after everything started. Can you even grasp a number like that? It feels like stretching the entire history of the cosmos across your cabin, only for this pivotal instant to be smaller than a speck of dust on your viewport, doesn't it? A truly wild scale. Here, in this cosmic infancy, the very fabric of space and time, along with all the fundamental forces, were inextricably tangled, a quantum knot we're still working to unravel. The universe then was impossibly small, condensed, and searingly hot. All the distinct forces we know today, gravity, electromagnetism, and the two nuclear forces utterly unified, indistinguishable, perhaps even a single, glorious superforce, within a churning quantum froth of pure energy and wildly curved spacetime. What a strange, magnificent beginning. Our science dreams of bridging that gap, of finally understanding that state. A theory of quantum gravity to weave Einstein's elegant tapestry with the strange quantum realm. Until then, it remains a radiant horizon, a boundary we can only approach with awe. But from this horizon, we can describe what gently unfolded next. As the nascent universe continued its astonishing expansion, and just as critically as it began to cool, these unified forces, once inseparable, commenced their subtle dance of separation. This quiet, monumental process is what we call symmetry breaking. Imagine a hot, swirling liquid slowly chilling, its molecules gradually arranging into a beautiful, structured crystal. That's a bit like what happened. First, gravity, that familiar force holding our ship together and our coffee in its cup, gracefully split off from the others. Then, the strong nuclear force, the binder of atomic nuclei, found its own distinct identity. And as temperatures continued their gentle descent, the electromagnetic force, which powers our console lights, and the weak nuclear force, essential for stellar fusion, politely parted ways as well. Each step brought new structure, new differentiation, and the emergence of fresh possibilities. Isn't that just like space? Always revealing new layers as you observe. One of the most dramatic changes surged into being just after these initial force separations. A moment of cosmic exuberance called inflation. According to this theory, the universe didn't merely expand in a measured way. It ballooned, quite literally, in an almost unbelievably tiny fraction of a second. Space itself, not matter, moving asterisk through asterisk space, stretched faster than the speed of light. Nothing to worry about, though. It wasn't a violation of relativity, just the canvas itself undergoing a phenomenal stretch. The sheer scale of this growth is mind-bending. In less time than it takes light to cross a single atom, our entire observable universe may have blossomed from a subatomic speck to something vast enough to contain galaxies. Why this sudden, explosive growth? We're not entirely sure, but a leading idea suggests a high-energy field, playfully named the inflaton field, briefly dominated the universe's energy. This field triggered that exponential expansion, then gracefully decayed, dumping its stored energy into the cosmos, creating a uniform bath of particles and radiation. We sometimes call this the reheating of the universe. And with that reheating, the stage was set for what we typically envision as the hot Big Bang. This was the true genesis of particles, of light, of the fundamental building blocks that would embark on their long journey toward forming stars, galaxies, and eventually us. After inflation quietly subsided, the universe was filled with an incredibly hot, dense plasma, a seething, energetic mixture of fundamental particles and pure radiation. From this raw energy, protons and neutrons began to coalesce, then swiftly combined into simple atomic nuclei. This foundational process, called primordial nucleosynthesis, unfolded in mere minutes after the beginning, meticulously determining the basic recipe for all matter in the cosmos, mostly hydrogen, a generous helping of helium, and trace amounts of other light elements. It's astonishing how much was decided in those frantic first moments, isn't it? The delicate balance between matter and antimatter, the universe's overall density, even the subtle seeds of structure that would one day blossom into galaxies. Much of it was baked in during this brief, chaotic period, governed by laws we're still striving to fully grasp. One thing is clear, though. By this point, the universe was no longer just a quantum fluctuation. It was a very real place, brimming with energy, motion, and immense potential. And yet, it remained frustratingly opaque. Light, despite its boundless energy, couldn't travel far. It was constantly bouncing off the charged particles, swirling in that dense plasma, trapped in a cosmic fog. The universe glowed, certainly, but not with the clear, visible light we know. It would take hundreds of thousands of years more, as our ship continues its silent drift, for the cosmos to cool sufficiently. Only then could electrons settle into stable orbits around atomic nuclei, forming the first neutral atoms, and finally allowing light to stream freely across the vast expanse. When that moment arrived, the very first photons of visible light began their epic journey through space. That ancient light, stretched by billions of years of cosmic expansion, is still with us today. We call it the cosmic microwave background, or CMB, and it's truly the oldest light we can possibly observe. Let's pause now and simply absorb its presence, this faint glow in the sky that isn't tied to any star or galaxy, but to something far, far older, something woven into the very fabric of space itself. Roughly 380,000 years after the Big Bang, just as the temperature outside our viewport might have dropped ever so subtly, the universe cooled enough for those electrons and protons to finally combine into stable, neutral hydrogen atoms. This momentous event, known as recombination, marked a dramatic and fundamental shift in how the cosmos behaved. For the very first time, light could travel freely, no longer trapped in that dense fog of charged particles. Photons began to stream outward across space in every conceivable direction, like the gentle spreading of dawn's first rays. That light, those very photons, are still traveling today. This is the CMB, a uniform bath of radiation that fills the universe, not in patches or streaks, but as a smooth, almost perfectly even glow, truly the faint afterglow of creation itself. You won't see it with your naked eye, of course. The immense stretches of time and expansion have elongated its wavelengths down into the microwave part of the spectrum, but it's undeniably there, surrounding us. A soft whisper of ancient heat, a silent testament to the universe's earliest moments. The discovery of this cosmic relic, in many ways, was quite an accident. In 1965, two radio engineers, Arno Penzias and Robert Wilson, were painstakingly working with a sensitive antenna in New Jersey. They certainly weren't searching for relics of the early universe. Oh no. They were simply troubleshooting a persistent, nagging noise in their instrument, a steady hiss that just wouldn't go away no matter what they tried. You realize they had inadvertently stumbled upon something monumental. They'd even tried cleaning out what they thought were pigeon droppings from their antenna, convinced some terrestrial interference was to blame. Imagine that. But the persistent hiss, that faint whisper, remained. What they'd caught, quite by accident, was the cosmic microwave background, the cooled, ancient light from the universe's very beginning. Almost simultaneously, across an ocean, a group of brilliant minds had predicted this exact glow should exist. When their paths finally converged, the weight of the moment was palpable. A quiet hum in the vast silence. The Big Bang wasn't just a grand idea anymore. It had left a clear signature, a cosmic map etched in the very fabric of space, still visible to us today. As you gaze out the viewport, the starlight reflections dance softly on the console, a gentle reminder of all the light that has traveled to reach us. At first glance, this cosmic background appears astonishingly uniform, like a perfectly smooth, ancient canvas. No matter where you might steer our ship, if you were to measure it, its temperature hovers at nearly the same chill, just a few degrees above absolute zero. Your console lights cast a soothing blue glow, the faint engine hum a constant lullaby. But then, as our instruments became exquisitely precise, capable of detecting the most delicate nuances, a remarkable detail emerged. That perfect smooth glow wasn't perfectly smooth, after all. There were tiny ripples, almost imperceptible shivers in the temperature, fluctuations so minuscule they were barely a millionth of a degree. Why does the universe always do this to you, hiding such profound secrets in the most subtle of details? These gentle undulations, known as anisotropies, were whispers of tiny differences in the early universe's density. In some cosmic corners, matter was packed just a breath more tightly. In others, it was a touch more diffused. Over the expanse of billions of years, gravity, the universe's great sculptor, would slowly amplify these minute variations, drawing matter together, coaxing it into forming the first galaxies, then stars, and eventually the planets we know. Without those delicate ripples, that cosmic tremor, there would be no structure at all, just a vast, featureless sea of light and gas. Think about that for a moment. No vibrant nebulae, no glittering starfields, no life, just ... nothingness, structured. So, you see, the cosmic microwave background is, in essence, a baby picture of the universe, a snapshot taken when it was a mere 380,000 years young, long before the first star kindled its fire, ages before Earth even began to coalesce. By carefully studying the shape and scale of those ripples, cosmologists can cleverly reverse engineer the ingredients of the cosmos. They can discern how much of everything ordinary matter, the mysterious dark matter, and even stranger still, dark energy, that enigmatic force pushing the universe ever outward, makes up this grand design. The recycled air stirs gently around you, a cool caress as we drift, feeling that ancient breath of the cosmos. One of the most dedicated cartographers of this early universe was the Planck satellite, launched by the European Space Agency over a decade ago. For several years, it meticulously painted the most precise image we've ever received of that primordial era, a glowing oval of subtle color shifts, each delicate hue marking a tiny difference in temperature and density across the cosmic sky. From this incredible data, we've learned our universe is approximately 13.8 billion years old, its expansion rate precisely measured, and we've confirmed that ordinary matter, the stuff of stars, planets, and even you and I, accounts for only about 5%. The rest, an invisible ballet of dark matter, pulling galaxies together, and dark energy, gently pushing the universe apart. Yet, even with all this profound insight, the CMB also marks a boundary. Not because there's nothing beyond it, but because it's the farthest light that has ever or ever can reach us. Anything earlier than this moment of recombination, when the universe cooled enough for light to travel freely, is still hidden behind a shimmering veil of superheated plasma. To peer further back, to truly glimpse those first moments, we'd need something other than light, something even older, something perhaps even more fundamental. And that, my friend, leads us toward the next great cosmic mystery. Not what we can plainly see asterisk, but what we can only gently infer asterisk. Let's reorient our view, shifting our thoughts back to the absolute earliest moments after the Big Bang, not focusing on the grand expansion itself, but on the infinitesimal things it left behind: pure energy, intense heat, and eventually the building blocks of matter. Here's one of those deceptively simple, yet profoundly deep questions. Why is there something rather than nothing? The universe is full of things. Isn't that just like space, always posing the biggest questions with the simplest words? The laws of physics, as we currently understand them, suggest matter and antimatter should have been born in perfect, elegant equality. For every proton, an antiproton; for every electron, a positron. And when these opposites meet, they embrace and vanish, returning to pure energy in a brilliant flash. In theory, the early universe should have been perfectly symmetrical, a grand, silent annihilation. Yet, clearly, it wasn't. When we look around today, you see a universe almost entirely composed of matter. Antimatter, while fascinating, is exceptionally rare, appearing mostly in particle accelerators or during powerful cosmic events. Somehow, in those first fleeting fractions of a second, matter gained a tiny, almost imperceptible upper hand. Not by much, mind you, perhaps just one extra particle of matter for every billion pairs, but it was enough. When all the grand annihilations were finished, that minuscule excess was left behind, and from that small remainder came everything. This fundamental imbalance, this quiet triumph of matter over antimatter, is called baryon asymmetry, and to this day, it remains one of the most intriguing open questions in physics. What tilted those cosmic scales? What made matter come out ever so slightly ahead? You might need a moment to just float here and ponder that. Physicists, in their ceaseless quest, have proposed several elegant mechanisms to explain this cosmic tilt. One possibility suggests that the very laws of physics aren't perfectly symmetrical, that there are subtle processes, quiet nudges, which treat matter and antimatter just a little differently. These are known as CP violations, charge parity violations, and, while they've been observed in certain particle decays, we haven't yet found one robust enough to fully account for the vast imbalance we see across the cosmos. Another idea involves heavy, exotic forms of matter that no longer exist, ethereal particles that might have decayed in asymmetrical ways during the universe's earliest infancy, favoring matter over antimatter by just the right tiny amount. These decays could have set the stage for everything to come, like a hidden hand guiding the cosmic dice. But these particles remain purely theoretical, fleeting whispers in the void. If they ever existed, they vanished almost instantly, leaving only their profound influence behind, a cosmic ghost story. Whatever the precise mechanism, the result was utterly profound. That slight, almost imperceptible excess of matter, perhaps just one part in a billion, would go on to form every atom, every molecule, every star you see twinkling beyond our hull. Without it, there would be no galaxies to drift through, no starlight to reflect on our console, no chemistry to form life. The entire visible universe, Every breathtaking vista, every quiet moment of wonder, is built on what might be described as a cosmic rounding error, a delicate imbalance woven into the very fabric of creation. And what's even more humbling, as you feel the soft vibration through the ship's hull, is this: we still don't fully know why it happened. We can describe it, we can measure its effects, but the underlying cause remains just beyond our grasp. It's as if the universe left us a magnificent clue, but keeps the key to itself. And so, the journey of quiet wonder continues. Here we are, suspended quietly in the vastness, watching the faint glow from the main console reflect in your eyes. Scientists, for centuries, have sought the most delicate of answers, peering into the deepest, smallest corners of existence, within the whisper of ancient particles or the faintest cosmic backgrounds, searching for why. Why is there anything at all? This isn't just a question for labs and equations. It touches a profound curiosity, doesn't it? Why does such a fragile universe, so precisely balanced, allow something as intricate as us to emerge? The answer, incredibly, lies in a whisper, a tiny cosmic whisper, a minuscule cosmic imbalance. The early universe almost, but not quite, erased. That leftover sliver, from that subtle, almost imperceptible tilt, something extraordinary began to stir. You can feel the soft vibration of the hull beneath you, a gentle thrumming that echoes the universe's own patient rhythm. Gravity, the great sculptor, began its slow, deliberate work. Imagine the densest, most minute regions of this nascent cosmic soup, ever so gradually, drawing in their surroundings, pulling them closer, warming, compressing. These weren't yet the dazzling beacons we know, but their destiny was sealed. The once smooth, featureless fabric of reality was beginning to gather itself, to ripple and clump, preparing for a grand, luminous transformation. But before those radiant orbs could ignite, before the spiraling grandeur of galaxies could even begin to dream of forming, and long before a single world could take shape, the universe had to journey through a period of profound quiet, a time without a name, truly one almost beyond our imagining. Cosmologists now call it the cosmic dark ages, and that is precisely where we are headed next, a silent, breathtaking descent into pure cosmic potential. The universe once had a brilliant, blinding light, remember? A luminous, primeval fog of photons released when the very first atoms finally coalesced. But that primal glow didn't last. It stretched and thinned, cooled by the relentless expansion of space and the passage of untold eons. What followed was an immense stillness, a profound darkness, a long cosmic night that endured for hundreds of millions of years. The recycled air within our quiet vessel feels crisp, almost cool, as if mirroring the vast emptiness outside. If you could have floated here during that era, gazing out, you would have seen absolutely nothing. No starlight, no planets, just an infinite, silent void, quietly, patiently preparing for its astonishing future. Then, after eons upon eons, millions of years patiently ticking past gravity, the universe's most enduring artisan completed its patient task. Those denser pockets of gas continued to pull more material inward. Tiny ripples in density, seated in the universe's earliest moments, began their slow, inevitable growth. These colossal hydrogen clouds deepened into knots of immense pressure and gathering heat, and at a critical point, a threshold we now understand so well from the stars we study today, fusion ignited. The very first stars, truly immense, perhaps hundreds of times the mass of our own sun, flickered into being like the universe's very first whispered thought. These were the pristine population 3 stars, born from pure hydrogen and helium, untouched by any heavier elements. They lived with a furious intensity, burning brightly and swiftly collapsing into either mighty black holes or spectacular supernova. Their light, powerful and brief, began to lift the veil of the cosmic dark ages. Not in an instant, but with a gradual, wondrous unfurling, you might notice the faintest, almost imperceptible shift in the ambient temperature, a subtle warmth as the universe stirs to life. As these initial stellar giants blazed into existence, they flooded their surroundings with torrents of ultraviolet radiation. This energetic outpouring began stripping electrons from the lingering neutral hydrogen atoms, transforming the cold, dark gas back into an ionized, shimmering plasma. This process, known as reionization, slowly but surely began to peel back the heavy shroud of darkness across the cosmos. It wasn't an overnight explosion of light, more like a slow, deliberate dawn, spreading unevenly across space. The first stars clustered into embryonic galaxies, carving out glowing, transparent bubbles in the dark, much like watching a mist slowly part, revealing the depths beyond. Over hundreds of millions of years, these luminous bubbles swelled and merged until the universal fog of neutral hydrogen largely dissipated. Space, at last, became truly visible again. Observing this ancient phase, from the first flicker of stars to the completion of reionization, is incredibly challenging, isn't it? The light from those distant nascent stars is impossibly faint, stretched across billions of light years. But now, magnificent new instruments, like the James Webb Space Telescope, are beginning to capture the merest glimpses of galaxies formed just a few 100 million years after the Big Bang, offering us our first direct look into that long-lost, glorious era. These earliest galaxies, though smaller, denser, and far more chaotic than the grand spirals we see today, were true cradles of starlight, powered by the elegant dance of gravity and fusion. With them arrived the universe's first truly complex chemistry, the very first heavy elements, the building blocks for absolutely everything that would follow. Imagine that the carbon in your skin, the oxygen in your breath, the iron in your blood, all traced back to these primordial furnaces. It truly is remarkable, isn't it? When those first colossal stars reached their spectacular end, they didn't merely fade away. Many detonated in brilliant, universe-shaking supernova, scattering their freshly forged elements across the expanding void. Carbon, oxygen, iron, silicon, these precious cosmic ashes seeded the next generation of stars. Around some of those new stars, subtle disks of dust and gas began to coalesce, swirling and colliding, slowly, patiently shaping themselves into the very first planets. The soft vibration through the whole feels like the pulse of creation itself. Galaxies, those swirling islands of stars, began their majestic assembly into even larger, more intricate structures. They collided, merged, and spun into elegant spirals and graceful elliptical forms. The vast, interconnected cosmic web, a filamentary network woven from dark matter and galaxies, slowly emerged. The universe, no longer smooth and dark, was now vibrantly alive with light, breathtaking complexity, and boundless motion. By roughly 1 billion years after that initial cosmic whisper, the universe had truly entered a new era. In its broad strokes, it had begun to resemble the magnificent cosmos we observe today, still evolving, still expanding, yes, but now brilliantly lit by billions of stars and exquisitely shaped by the enduring hand of gravity. The long, deep silence was over. The grand symphony had truly begun. As the universe matured, just a few billion years into its existence, it started to look familiar, at least from our distant, timeless perspective. Galaxies had fully formed, glowing with the brilliance of countless stars threaded together by gravity into immense, interconnected structures. Some danced in elegant spirals, while others clustered into tight, radiant knots. Great, dark voids stretched between them, like vast, empty bubbles in a cosmic foam. The universe, once so uniform and dark, had now transformed. You might feel a subtle tremor, a gentle thrumming deep within the ship's frame, a constant reminder that you are moving, ever so slowly, through this magnificent, ever-stretching canvas. Gaze out at the distant pinpricks of light. They twinkle, but something about their color feels ... off, doesn't it? A faint, reddish hue, as if a cosmic filter has been placed over the universe. This isn't just an illusion. It's the signature of space itself, unfurling. Every galaxy, every distant cluster, is slowly drifting away from us, carried by the invisible tide of the universe's expansion, which has been pushing outwards since time began. Their light, stretched and thinned over eons of travel, whispers a secret. The more remote they are, the faster they recede, their vibrant white light subtly shifting towards the warmer, longer wavelengths of red. Isn't that just like space, always finding a poetic way to tell its story? For the longest time, we human voyagers, gazing up from our small blue marble, simply assumed this cosmic stretching had to be slowing down. It just made sense, didn't it? Gravity, that invisible hand, pulls everything together. With so much matter scattered across the void, surely its collective pull would act like a cosmic brake, gradually bringing the expansion to a halt. Some even whispered of a big crunch, a grand reversal, where the universe might one day fold back in on itself, collapsing into a single, unimaginable point, like a breath drawn back in. You can almost feel the gentle shift in the ship's internal gravity, as if it's hinting at such vast, profound movements. But then, only a few decades ago, astronomers peered deeper into the velvet dark, studying distant, spectacular stellar explosions, supernova so bright they could serve as cosmic lighthouses. And what they discovered, well, it sent a ripple through the quiet hum of scientific understanding. The universe wasn't slowing down at all. Oh no, it was actually speeding up. Imagine the quiet gasp, the collective wonder. Some elusive, unseen presence was actively pushing everything further apart, accelerating the very fabric of existence. We've given it a name, a hushed whisper in the dark, dark energy. Doesn't it sound rather enigmatic? This dark energy isn't something you can touch or observe directly, not like a nebula you might drift through, feeling the subtle temperature drop as you approach. It doesn't glow, it doesn't clump together like matter, and it certainly doesn't behave like anything we're familiar with. Instead, it feels more like an inherent property of space itself, an energy woven into the very vacuum, gently nudging everything, every star, every galaxy, away from everything else. It's the dominant force out here, comprising perhaps 70% of everything. 70%. Yet its true nature remains shrouded in cosmic mystery. Is it constant? Does it ebb and flow like the tides? Why does the universe always do this to you? Offer such profound questions with no easy answers. Its effects, though, are undeniably profound. You can almost sense it out there beyond the viewport. a silent, pervasive pressure over unfathomable stretches of time. Those galaxies not bound tightly by gravity will simply drift further and further away from us, until eventually their light will be so stretched, so distant, that it will never reach our eyes. They won't be moving asterisk through asterisk space. Rather, space itself will be expanding so rapidly that they'll simply slip beyond our horizon of visibility. The universe, which once teemed with the bright, buzzing energy of countless clusters, might become a colder, lonelier expanse. Only the closest, most gravitationally bound neighbors will remain in view, like familiar faces fading into the deep, quiet night. Even in that quiet isolation, the cosmic dance will continue. Stars, like weary travelers, will age and eventually fade, collapsing into dense white dwarfs, spinning neutron stars, or ravenous black holes. Others will be born from the scattered stardust of earlier generations, a continuous cycle. But over truly immense timescales, trillions of years perhaps, the cosmic fuel will dwindle. Star formation will slow to a whisper, fewer and fewer new lights igniting, until the galaxies themselves grow dim. One by one, like candles extinguished in a vast hall, their brilliance will wane, and the universe will ease into what some call the degenerate era, a time where only the silent remnants rule, white dwarfs drifting, black holes swallowing slowly, time itself stretching on without end. Eventually, even the mightiest black holes, those cosmic titans, may slowly evaporate, dissipating their energy over eons through a peculiar phenomenon known as Hawking radiation. And if that gentle, accelerating push of dark energy persists, the universe will continue to thin and cool, approaching an absolute stillness, a quiet equilibrium. No stars, no warmth, just a diffuse, almost imperceptible scattering of particles in an endless expanse. It sounds stark, doesn't it? But remember, this is just one possibility, one path the cosmic river might take. The future, my friend, is vast and brimming with quiet questions, just like the space we drift through now. The universe, you see, has never been static, not for a single moment. From that first unimaginable spark of the Big Bang, it has been a canvas of ceaseless change. Particles coalesced, light broke free, galaxies spun into magnificent being, and stars, like brief, brilliant blossoms, lived and died in countless cycles. Even now, billions of years later, as you feel the subtle hum of your ship, everything out there is still in motion, still unfolding. But what truly lies ahead for this grand cosmic tapestry? It's a thought that makes the quiet hum of the engines feel even more profound, doesn't it? If that dark energy, that quiet, accelerating force, continues to behave just as it does today, then our universe is indeed destined for a colder, darker destiny. This outcome has a fittingly gentle name, the Big Freeze. Imagine it, an endless expansion where all the stars eventually exhaust their fiery hearts, burning out one by one. The black holes, too, would eventually vanish, leaving behind only an incredibly thin, silent fog of elementary particles, spread infinitely across an ever-growing void. It won't be a dramatic catastrophe, no fiery crash or explosive finale, just a long, slow exhale into an eternal stillness. Nothing to worry about, probably. But the Big Freeze is not the only story whispered among the stars. Some theorists ponder a different fate, a more dynamic one, where dark energy doesn't remain constant, but actually grows stronger, over time. In this scenario, the universe's acceleration would relentlessly increase, slowly inexorably, tearing galaxies apart first. Then, like pulling threads from a tapestry, it would unravel individual stars, then planets, and eventually, even the very atoms that compose you and me. This is the chilling concept known as the Big Rip. It wouldn't be a sudden, violent event. Oh, no. It would unfold over billions of years, a slow, unstoppable dissolution. But in its final, terrifying moments, space itself might become so utterly unstable, stretching so rapidly, that nothing, absolutely nothing, could remain bound together. Even the smallest, most fundamental building blocks of matter might be ripped apart, scattered into an inconceivable nothingness. It's a far more dramatic vision, perhaps, and still deeply speculative, but it follows a certain cold logic. If dark energy itself is destined to evolve, then again, perhaps this grand expansion won't continue forever. Isn't that just like the universe, always keeping us guessing? Some cosmological models propose that dark energy might, at some point, reverse its insidious push. The universe, having stretched to a certain cosmic limit, might then begin to slow, hesitate, and eventually, gently, collapse back inward upon itself. A reversal of the Big Bang, indeed, a big crunch where everything is drawn back together. Heat would rise, density would intensify, until perhaps another immense explosion might ignite, beginning the cosmic cycle anew. From this, some have envisioned a universe that breathes, oscillating like a vast, living entity, a cyclic cosmos, forever expanding and contracting. This ancient idea, whispered in myths long before our science could give it form, suggests a cosmos ... And as we continue our gentle drift, you might find yourself contemplating that the universe, much like our journey, might not have a true starting point or a definitive end, but merely an endless series of beautiful transformations. Consider it a cosmic breath, where immense collapses might just be the prelude to breathtaking new expansions, and what we perceive as deaths of old systems simply pave the way for vibrant, energetic births. It's a cyclical dance, playing out over unthinkable stretches of time, where even the most brilliant minds back home now acknowledge the possibility. The faint thrum of the ship's engines, a steady lullaby against the vast silence, seems to echo this very rhythm, a testament to enduring motion. Some of the keenest minds, those who dedicate their lives to the stars, whisper of theories like loop quantum cosmology, suggesting our Big Bang wasn't a solitary beginning at all, but perhaps a cosmic bounce, a spectacular rebound from a universe that came before, collapsing back in on itself. Others paint even grander pictures, envisioning entire multiverses, our familiar cosmos, just one delicate bubble suspended among countless others, or new regions of space continually flickering into existence, far beyonders, far beyond with Srians through the depens prums plembum de sanio, in pro plan with stella so, giam havenime sala. To go, to talk, Are these visions testable? We don't yet know. They remain at the farthest edge of human understanding, shimmering like distant nebulae, born from elegant mathematics and profound physics, offering something deeply comforting, the sense that this grand story is far from over. Why does the universe always do this to you? It always leaves you wanting more. But even with such boundless futures stretching before us, the present moment is undeniably real, isn't it? You are here, now, in this luminous sliver of time, balanced between the deep, unwritten history before and the tranquil silence yet to descend. The universe's eventual fate stretches out, truly incomprehensible, far past the lives of stars, beyond the turning of galaxies. It's a canvas painted not with earthly pigments, but with the raw forces of motion, shifting temperatures, and the very fabric of space itself. While we may never gaze upon its ultimate destiny, you, in this quiet vessel, are intrinsically part of its unfolding present, a tiny, luminous ripple in an ocean of ceaseless change. Nothing to worry about, probably, your existence. Gently supported by artificial gravity that subtly shifts, connects you to this grand narrative. You live on a world cradled by a star, orbiting within a galaxy, all of us gracefully adrift in a universe that blossomed from intense heat and will one day resolve into a profound quietude. The very forces that once sculpted the early cosmos continue to choreograph its future, guiding the distant stars you see reflecting off the main viewport. Isn't that just like space, mirroring itself? To truly study these boundless realms isn't just about looking outward. It's about understanding ourselves anew, recognizing our integral place within something so vast, so ancient, and so utterly persistent. We are not mere spectators. We are a brief, vital line in its endless, unfolding poem. And so, we've journeyed through these ideas together, tracing a thread from the initial spark of time, through the quietude and the brilliant stars, to the very edge of what might yet be. We've pondered particles, too tiny for sight, and distances so immense that light takes billions of years to traverse them. We've navigated the depths of darkness, not as a source of fear, but as the generative canvas from which all wonders emerge. If you're still awake, perhaps you're simply resting, allowing the majestic shapes of galaxies to softly imprint themselves behind your eyelids. Or perhaps you've already begun to drift, carried into that serene space between memory and dream, gently propelled by currents of starlight and quiet curiosity. Wherever you are in this soft, unfolding moment, thank you for joining this silent voyage. As you rest beneath these quiet stars, while distant galaxies continue their slow ancient waltz, in the profound darkness, and photons from epochs past whisper across the boundless sky, just remember, the universe continues its grand narrative. It's still unfurling, still drifting, still softly singing in the timeless language of space itself. And so, under this deep, dark silence, the story continues.